Imagine a clock that never needs winding, a pendulum that swings forever without losing a single ounce of energy. It sounds like something straight out of a steampunk fantasy novel, right? For centuries, scientists told us this was impossible because of the laws of thermodynamics. But what if I told you that the universe actually has a loophole? Today, we are stepping into the strange, shimmering reality of the time crystal. Welcome to SciNova, where we explore the edges of what is possible. If you've ever felt like time was slipping through your fingers, you're about to find out that time can actually be captured in a solid form. We aren't talking about time travel in the Hollywood sense, but something much more fundamental. We are talking about a state of matter that defies our most basic intuitions about how the universe moves. To understand this, we first have to talk about symmetry. In physics, there is a concept called time translation symmetry. This basically means that the laws of physics don't change whether it's Tuesday or Friday, or whether you perform an experiment now or 10 minutes from now. Most things in the universe respect this rule. If you kick a ball, it eventually stops due to friction and energy loss. The system settles into a predictable, static state. Enter the genius of Nobel laureate Frank Wilczek. Back in 2012, Wilczek proposed a theoretical possibility that sent shockwaves through the physics community. He suggested that a new kind of structure could exist that spontaneously breaks this time translation symmetry. Essentially, he theorized a system that would change its state periodically, even when no external force is acting upon it. It was a mathematical, beautiful idea that seemed almost too weird to be real. Now, before you call this perpetual motion, let's clear the air. Many people hear moving forever and immediately think of a machine that creates energy out of nothing, which would violate the second law of thermodynamics. But time crystals are different. They operate in non-equilibrium systems. They aren't creating new energy. They are simply existing in a state where they repeat a pattern without needing an external push to keep the cycle going. They are effectively stuck in a loop of motion. The theory was brilliant, but was it real? For a few years, it remained a beautiful mathematical ghost. That changed around 2016 and 2017 when researchers finally achieved the impossible. In highly controlled laboratory environments, scientists observed the first discrete time crystals. They weren't just looking at math on a chalkboard anymore. They were looking at actual matter that pulsed with a rhythmic, internal beat that refused to die down. So, how do we visualize a time crystal? Think of a regular crystal, like a diamond. In a diamond, atoms are arranged in a repeating pattern in space. If you move from one atom to the next, the structure looks the same. A time crystal is like that, but the repetition happens in time. Imagine a structure where the atoms don't just sit there, but they flip or change their state at regular intervals, creating a pattern that repeats through the dimension of time itself. We've moved from the discrete version to something even more profound. Recent breakthroughs have pointed toward the existence of continuous time crystals, or CTCs. While discrete crystals pulse like a heartbeat, CTCs are characterized by the spontaneous breaking of continuous time translation symmetry. This means the pattern isn't just a series of clicks. It's a smooth, continuous flow of periodic motion that exists within the very fabric of the system's state. This brings us to the deep dive. Why does this matter? Why should we care about a tiny, pulsing quantum structure that seems to serve no purpose? The answer lies in the future of technology. We are currently living in the noisy era of quantum computing. Quantum states are incredibly fragile. The slightest heat or vibration can cause them to collapse, a phenomenon known as decoherence. This is the biggest wall standing between us and a true quantum revolution. This is where time crystals become the heroes of the story, because they are naturally stable in their repeating cycles. They could potentially serve as long-lived memory elements. Imagine a quantum computer that doesn't forget its data every microsecond. Instead, it uses the inherent rhythmic stability of a time crystal to protect and store quantum information. They are like biological rhythms for machines, providing a steady, reliable beat in a chaotic quantum world. Beyond memory, there is the potential for ultra-precise frequency standards. In science, everything depends on how accurately we can measure time. From GPS satellites to deep space communication, precision is everything. If we can harness time crystals as quantum clocks that are naturally resistant to environmental noise, we could achieve a level of measurement precision that is currently unimaginable. We are talking about clocks that don't just keep time, but define it with absolute stability. It is important to remember that we are still in the early stages. We aren't building time crystal-powered spaceships just yet. The challenges of scaling these systems from a single laboratory observation to a functional technology are immense. We need to master the control of non-equilibrium systems at a scale we've never seen before. But the foundation has been laid. The door to this strange new room in the house of physics has been cracked open. So, what have we learned today? We've learned that time crystals aren't a violation of the laws of physics, but a stunning demonstration of how complex those laws can be. They break the symmetry of time without breaking the laws of thermodynamics. From Frank Wilczek's 2012 theory to the laboratory breakthroughs of 2017, we are witnessing the birth of a new way to understand matter. The universe is far more rhythmic and strange than we ever dared to imagine. If you found this journey into the quantum realm fascinating, make sure to hit that subscribe button and ring the bell. We are constantly diving deep into the mysteries of the cosmos, and you won't want to miss what's coming next. What do you think? Could time crystals be the key to the next technological leap? Let us know in the comments below. Thanks for watching SciNova, and keep staying curious.